All right, welcome back. You've made it to part four, the last in the four-part series on Bernoulli's equation. So in this one, I'm going to show a couple of examples that may line up or clash with your intuition, depending on your proclivity. And then I will wrap up with a neat little table that Dina has graciously provided. So let's get started. The first example I want to give is one of the vertical current carrying pipe. So there's no pumps, no resistance in here. It's just a vertical current carrying pipe. Now, what I want to ask you is basically like, what happens? What parts of the Bernoulli equation change when I go from this initial position up top to this final position at the bottom? So gravity points down here. The ground is down. There's the ground. And here's gravity pointing downward. We'll put a sun up in the sky. All right, call it a sun, whatever. Okay, so which of my terms are changing in this situation? Well, I've got current that's flowing down this pipe. The pipe is oriented downward, so it's dropping in height. So we're going to have our gravity head term change. That one's changing. Um, I've also got no pump. I've also got no resistance. So this side is 0. Now, my initial thought is, if it's kind of like with any other thing that you just drop from one height to a lower height, I'd expect that the velocity at the lower side would be higher than the velocity at the upper side. Let's check that. So I've got rho g delta y. Rho g delta y. Is height increasing or decreasing? Well, height is decreasing. So delta y is going to be a negative number. So delta p plus rho g delta y plus 1/2 rho delta of v squared equals 0. This is going to be a negative number because our height is decreasing, rho is a positive number, and g is just the positive constant for gravity. So delta y is the thing bringing in that negative here. So the question is, in order for this to equal 0, are both change in pressure and change in speed positive? Or is it only one? Is one negative, one positive? To resolve this, we actually can't just Rayleigh appeal to this situation or this equation alone, not just Bernoulli's equation here. We actually also have to bring in continuity. So if this is just your typical piece of PVC from the hardware store, the two areas, A1 and A2, are the same. We've got the same areas in this little cylindrical piece of pipe. So what does that mean? If I look at continuity, I2 equals I1, if A1 is equal to A2, that means that their velocities must also be the same. So it can't be a change in velocity. So again, if A1 is equal to A2, let's write. If A1 equals A2, then by continuity, V1 has to equal V2. They have to be traveling at the same speed. The fluid flow has to be traveling at the same speed in both positions. So, yeah. What does that mean? It means delta V squared is 0, which means, in fact, it's the pressure that increases, not the speed in this vertical pipe. So, yeah, it's kind of, again, this one for me was a bit of an intuition breaker when I first saw it. If I have a vertical pipe that's just carrying water down, the pressure is the thing that's increasing. The velocity can't change because it's constrained by continuity. Continuity. In other words, conservation of volume. The next example I want to talk about is a way to measure pressure in a fluid system. So you can see here I have two pipes. I have a horizontal pipe, which carries some current, I'll say from left to right, and I have a vertical pipe, which contains some water, or contains some fluid, I should say. Now, the top of this pipe is exposed to atmosphere. That's pretty important. So here's the surface of the fluid. There it is. And there's the atmosphere up here. Atmosphere up here. So this is an example in DLs. I want to give you some hints, basically. So here's my hint. At the top of the at the top of the vertical pipe, we have two fluids that are in contact with one another. We have the air on top, and we have the water on the bottom, let's say, or the fluid. I'll call it water. So what I'm interested in, call this initial and this final, what I'm interested in is determining what quality these two materials share, these two things, the air and the water. So if we just look at our equation, considering our 2 points, we have no resistance. There's no, rough pipe or anything in here. We have no pump between these 2 points, even though it's two different fluids. And we have essentially very little change in height. I had to draw them a little bit separate from one another, but what I really mean is just a point slightly above the interface and slightly below the interface. So essentially no change in height. And each of these things has approximately speed 0. This water is just standing still in this section of pipe. It's not spurting up, it's not spurting down. Similarly, the air isn't spurting, in toward the pipe, it's not spurting up. So there is no velocity in this direction. V is 0. Okay, so what does that show us? It shows us that the difference in pressure between these initial and final points is also 0. Delta P at the top interface is also 0. So the pressure at this top point, in the fluid, P fluid top, is just atmospheric pressure, 101 kilopascals. So this is useful to me because I can use this height of the pipe, of the still standing water in this vertical pipe, to measure the pressure down at the bottom in the pipe itself, in the pipe proper. So how do I do that? Recall that the fluid flowing through this pipe has some pressure, and that pressure corresponds to a force on the walls of the pipe. If I give the water some room to expand, so say it enters this region here where we've got this upper pipe now, the water is going to expand upward to fill up that space. Yeah, so one way I can get a handle on the amount of pressure is the amount of pressure at the lower part of the pipe is by now considering these 2 points, the point right below the interface and the point right above the rest of the fluid flow. So in this region, recall, no water is actually circulating through this upper section. It's just kind of standing there. It's getting propped up by the current underneath it. So between these 2 points, if I again look at my equation, let me erase these bad boys. There we go. So I again have no current, sorry, not no current. I have no resistance and no pump between these 2 points. Velocity for each is just 0. There's no current in this upper pipe, and we're considering a point in the upper pipe in both cases. There is a change in height, and there should be a corresponding change in pressure. So this is a way that I can use the height of a standpipe, or the height of a vertical pipe, branching off from a main pipe to determine the pressure inside that lower pipe. In other words, delta P, which is going to be P final pressure minus P initial, which is the atmospheric pressure up at the top, is just going to be negative rho G delta Y. Okay, let's move on to the last one. Resistance in a closed pipe. So what I want to do here is just show the effective resistance a little bit more quantitatively. And again, this can't be an intuition breaker. I think the biggest takeaway from this example is that resistance does not change fluid flow. Again, it doesn't change the current. It just typically changes pressure. So because of, or in a closed pipe, it does not change current. It just changes pressure. So imagine, if you like, I've got some fluid, again, moving this way. Here's my eye. I've got some cross-sectional area A throughout the pipe. We'll call it the same cross-sectional area just for fun. And I've got a rough section of pipe here that has some resistance R. Then the equation yields me, let me go grab it real quick. Okay, got the equation now. So let's set up some initial and final points. I'll set my first point, my initial point, to be before the resistance, and my final point to be after the resistive area. So the area between these two, initial and final, does include a resistive section, so this will stay with us. There is no pump between them. This goes away. There's no height change. They're both at the same horizontal height. We can think a little bit about velocity again here. So the area is staying the same from the left side to the right side. A1 equals A2. And by continuity, this means that V1 equals V2. Recall, continuity just says that the volume passing through the first cross-sectional area here has to be the same as the volume passing through the second cross-sectional area here, or A1 V1 equals A2 V2. Okay, so no change in speed, which means that in a closed pipe, a closed horizontal pipe, what resistance tends to act to do is decrease pressure. So a resistive pipe, if I had a pressure of, I don't know, say like 400 kilopascals over here, maybe by the time it comes over to the other side for a given amount of current, it reduces down to like 300 kilopascals for the appropriate numbers, for the appropriate amount of current. Notice also that the change in pressure scales linearly with the amount of current. So the more fluid I'm trying to push through my system, the more the pressure drop is going to be for a given like uniform resistance section of pipe, rusty pipe. The last thing I wanted to leave y'all with was just a quick summary of the terms of the Bernoulli equation. This table was created by Dina. Shout out Dina if y'all have seen her around the physics department or in previous lectures. So in the first column here, we've just got the names of each of the energy densities. If you refer to them by these names, we'll know what you mean. Also, if you call them like pressure head, kinetic head, etc., we'll know what you mean. In the middle, we've got the indicator in the style of energy diagrams. Ooh. So if you notice any of these things in a problem, there's a good chance that those are going to be relevant terms. And finally, the expression in the equation, just again, trying to make those links between each term and the relevant physical quantity. Okay, I think I'm going to call it there. Thanks for watching. Hopefully these were useful. Please do hit me with feedback. I'll probably make a short survey to see what y'all think of these first round of lectures, what to improve. And I'll catch you in the next one.